Hi, Calculus crew. Here's a very low-tech discussion on finding an area between a curve and the x-axis. I believe that you've seen some approximations where we put some rectangles under the curve and say, okay, we could approximate the area with these rectangles. We'll get a little bit more specific with this discussion here today. So for the example, I'm just going to use the graph of f of x equals x squared plus 4, and I'd like to find the area between the curve and the x-axis on the interval from x equals 1 to x equals 3. So we'd be looking for this area in here. And you can kind of tell by the shape of it that, maybe if we just put in a trapezoid, we could get a really nice approximation there, but we can do better than that with some tools that we've already seen, and with a few extra nudges from some new tools, we can get to the exact area. So this is the function we're going to work on today. This is the interval from 1 to 3. I just have this lowest spot labeled there from 0 to 4. It's not really going to play a role for us. To get a feel for what we're going to do, here's another picture of exactly the same curve. I'm going to put rectangles in here, and I'm going to make sure that the right-hand upper corner, right over there, this right-hand corner on the top is on the curve. So I know that you've looked at some exploration work where they've used the left-hand corner instead, or they've used the midpoint. The right-hand corner is really very favorable in terms of setting up a limit. So I'm going to use those right-hand corners, but you would get exactly the same result if you used the left-hand corner or if you used a midpoint variation on this. So that's going to be our plan. We're going to make equal-sized rectangles. And when I say equal sized, I don't mean the area of them. I mean the bases of them, these little widths down here. We'd like to set up a sequence of rectangles, all of equal width, that span the distance between x is 1 and x is 3. We'll find the areas of each of those rectangles, add them all up, and that would be an approximation. As we let those rectangles get narrower and narrower, we get better and better approximations. So to make this happen, we need to keep a couple things in mind. One thing to keep in mind, here in my low-tech demonstration, we're going to have some guest appearances by index cards. One thing to keep in mind is that if I wanted to find a total area of a sequence of rectangles and they all had width w, I could use the height of the first one times its width, plus the height of the second one times its width, plus the height of the third one times its width, all the way till we get to the height of the last one, the nth one, times its width. And that could be rewritten if we factor out the width, because that width is the same all the time. If we put that width outside as a factor and then just add up all of the heights. And that's what this notation is, the sum of the first n heights times the width, which is fixed. So summation notation is going to come into play. We're going to have a bunch of heights that vary, but the width is not going to vary. So we're going to need that idea. Just kind of hold that thought. We're going to have to add up some sums like this, so we need some formulas. One of them that we'll use is this one. This says, let's add up n copies of C. That's what this one means. And n copies of C is C times n. So you're going to store that for later. We'll also need this one. The sum of the first n integers is what this one means. When I runs from 1 to n of just I, it means add up 1 plus 2 plus 3 plus 4, all the way till we get to n. The formula for that, so that we're not having to add this up one thing at a time, will be that top value of n times n plus 1 divided by 2. There's a few different interesting proofs for how this works. There's a nice geometric one that I really like if you're interested in looking that up. Another one that we'll need will be the sum of the first n squares. So 1 squared plus 2 squared plus 3 squared, all the way to n squared. And the formula for that, first n squares, will be n times n plus 1 times 2n plus 1, all divided by 6. So we're going to store that information. We're just going to kind of keep it handy. All right, off we go. These take me a lot of paper. To get our area started, I'm going to use approximately for just a moment. Our area is approximately, Let's pretend that we had n rectangles that we wanted to put in here. If we have that situation where we're going to smush n rectangles in this segment between 1 and 3, that means that the width of each of the rectangles will be 3 minus 1 for a gap of 2 units divided by those n rectangles. So each of our widths will be 2 over n. And then I need to know each height. Well, the first height is not going to be related to x equals 1. It'll be related to x equals 1 plus a little nudge for that width because I want to put the right-hand corner on there. And then the next height is going to go with x equals 1 plus 2 nudges to get me there. And when I know those x values, I have to take them and put them into the function, x squared plus 4. So things are going to get a little sticky here. But hang with me. You're tough. We can make this happen. All right. So if we just write down one of the heights, it'll be our function evaluated at 1 plus, because that 1 is the left-hand edge. We need to give it a little nudge. The first little nudge would be 2 over n. The next little nudge would be 2 sets of 2 over n. The third little nudge would be 3 sets of 2 over n. Those are hard to say. So what we get for our x values that we're always evaluating is this starting value of 1 plus a certain number of nudges of 2 over n. I is going to run from 1 to 2 to 3 all the way up to n. Notice that when the I value equals n, we'd have cancellation here, and we'd end up with 1 plus 2. So we'd be talking about f of 3, which would be a right-hand corner on our last rectangle. So we need always to find these heights. That's what those are. And then we have to multiply by the width of 2 over n. That will give us height times width will give us an area. But I don't need just one of these. I need a lot of them added up. And so we get the summation. The sum from 1 to n. I have this approximately here because I'm saying we're going to use a fixed number of rectangles, but I haven't declared what that is yet. So we start like this, and then we need to get into some algebra. I want to take this 1 plus 2 over n times I and put it into the function. Our function was f of x equals x squared plus 4. So a little approximately here. I is 1 to n. Maybe a big set of parentheses would be good. We need to take 1 plus 2 over n times I and stuff it into that function. The input gets squared, and then we add 4. And then we need to multiply that by 2 over n. And if you're thinking, oh my, it's looking messy and complicated, like, yep, it is, but we are here together. You're going to be fine. I need to evaluate this inner portion. I need to expand it. Expanding will actually really help with that. And so here comes a guest appearance by an index card. If we do just this part in the first giant set of parentheses, just this, here's what I think we should get. Take the quantity and square it, which means the quantity times itself. We're still having that plus 4 hang around. You'll come through and do all of the distribution and all of the cleanup, just like you would for something like x plus 7 squared. And when you do that, I think you'll get 1 plus 4 over n times I plus 4 over n squared times I squared plus another 4. And then a little bit of cleanup with the like terms. The 1 and the 4 can combine to give you 5. And we'd be at 5 plus 4 over n times I plus 4 over n squared times I squared. So let's take that back to our approximation for area. And let's keep going. So this is going to go. I'm going to move this up. All right. So still area, big sum, I is 1 to n. We have things that we need to copy down. We had that 5 plus 4 over n times I plus 4 over n squared times I squared. That was that chunk. And we still have this 2 over n. These are expressions for our height times our width. So we're finding area. What we are really going to do, instead of making an approximation, is we're going to say, okay, the area is actually the limit as n goes to infinity of this sum. So we're going to let our n head off to infinity, and that's one of the reasons why we worked with limits at infinity recently. So we're going to carry this limit notation with us now that we have everything set up. I take a long time to copy stuff. Let's go ahead and run this 2 over n through the parentheses. So you'll get something that looks like this. 5 times 2 over n will be 10 over n. 4 over n times 2 over n in the second term would be 8 over n squared. 4 times 2, n times n, and then we still need the I hanging around. And then 2 over n times the third term, 4 times 2 is 8. N squared times n is n to the third, and then we have the I squared. So we multiplied the width all the way through. When we do these sums, we can split them into the sum of the first part plus the sum of the second part plus the sum of the third part. So we could really have 3 limits as n heads off to infinity, and that's where we're going to go next. So 10 over n for the first one. The limit as n heads to infinity of the sum, 8 over n squared times I, plus the limit as n heads off to infinity of the sum of I equals 1 to n, 8 over n cubed times I squared. Now we have some limits to rewrite, and that's where'd my little note cards go? That's where these are going to come back into play. All right, so that's why I said we're going to need those. Have them handy, store them. The n is going to head up to infinity. What we really need to do in this first sum is figure out the sum of n copies of 10. This one, we really need to worry about the formula for the sum of the first n integers. This one, we really need to worry about this part. These other portions, like 1 over n and 8 over n squared and 8 over n cubed, are really like coefficients that we pull out front. Once we declare an n, this would not vary anymore. It's really the I that runs through that iterative. First it's 1, and then it's 2, and then it's 3, all the way to the very end. So let's see if we can get a rewrite here. We still haven't taken a limit, so those limits stay in place, but the sums can go away. One of our note cards early on was this one. If we have n copies of something, this will be n copies of 10. So this will be 10n over over n. Plus, next one, limit as n goes to infinity. We're going to leave the 8 over n squared just like it is. And then I need the sum of the first n integers for that. And that was n times n plus 1 all over 2. And then we head off to the next one. The limit as n goes to infinity. We're taking care of the sum by writing down that thing that's acting like a coefficient, 8 over n cubed. And then we need the formula for the sum of the first n squares. And that was n times n plus 1 times 2n plus 1, hardly fits, over 6. Shoo. I promise you we're pretty close to being home with this one. Let's see what some good stuff is that happens. So in this first part, the n cancels. Ta-da! Here's one chunk. Some really nice things happen. So this is the limit of 10 as n heads off to infinity. That's just 10 plus. For the next one, usually what we would do is we would expand this all out and then divide the numerator and the denominator by the highest power of n squared, because we're dealing with something that's a lot like a rational function where we had polynomials in the numerator and in the denominator. Another kind of slick way to view this, and this is how I think of these, is I just look through and pretend like I'd multiplied this all out. And if I did, my leading term would be 8n squared. So I'm just going to write that down, 8n squared. When you have a polynomial and you're letting the variable go off to infinity, the only term of the polynomial that really has any power as your value of your variable gets bigger and bigger and bigger is that leading term. So that's the only one I focus on. The others aren't important. They don't have a whole lot of value when we're out toward infinity. So I just keep the 8n squared. Down below, if I multiplied those two together, I'd have 2n squared. Heading off to the next one. If I multiplied this all together, down below you can see the 6n cubed pretty readily. But up top, if you multiplied it together, the 8 is important, the n, and the 2n. If you were to multiply all of that out, your leading term in that polynomial would be 8 times 2 is 16, n times n is n cubed. So this would be 16n cubed. And you might have forgotten what we were looking for here. We're looking for an area, that area under the curve. I have one chunk, I know it's 10, but these other two chunks I still need to do the limiting idea with. So I was finding some expressions for limits there. And now you can notice, oh, the n squareds are canceling and the n cubes are canceling. And now when we go take a limit, 10 plus 8 divided by 2 will be 4. There's no more n hanging around with us. If we do 16 divided by 6, maybe if you reduce it a little bit, you'll get 8/3. And when we add this together, here's 14 plus 8/3. This is 2 2/3, so this is 16 2/3. This is supposed to be the area underneath our curve and above our x-axis. And this is how we would find it using limits. Shoo, right? It's a lot of stuff. It's a lot of notation. But we could, if we had to, we could work our way through this with a polynomial and we could figure it out. But let's see if what we would get with antiderivatives and integration will give us the same thing. So we may or may not have seen this yet, but let me put it back over here. Let me come over here. Depending on where we are in the class right now and where you are with watching tutorials, you may or may not know that when we find the antiderivative of something and we put boundaries on that from 1 to 3, that we're really finding the area under the curve. So if I wanted to find this area, I could say, okay, let's integrate the function that we're given from lower limit of 1 to upper limit of 3 with respect to x, and then we would go do that. We'll find the antiderivative first. That'll be 1/3 x to the third plus 4x, and you can check me on that. We're going to evaluate this expression at our upper limit of 3 first, and then subtract the expression when evaluated at 1. So if we do this, you'd get 1/3 times 3 cubed plus 4 times 3. That's plugging in the upper limit all the way through. And then subtract off whatever happens when you plug in 1 all the way through. And let's see, 1/3 times 1 cubed plus 4 times 1. Let's come back and do it. This is 27 times 1/3, which is 9. 4 times 3 is 12. Minus, well, let's see. This would have been 4 and 1/3. So let's see, this is 21 minus 4 and 1/3. 21 minus 4 is 17, and then take off another 1/3, and you would get 16 and 2/3. So this process is how we get the area using antiderivatives and a definite integral. And that other thing that we did that was really long, all of this over here, this is how we get the same answer using summation, which adds up a whole infinite number of little rectangles that we use to approximate the area under the curve. When we let the limit happen, we get exactly the same area. I know which one I would rather do with my time, but I want you to know that this is how it works behind the scenes. I also think that it's really important that you know how to set this up and what is happening, because that will help you grow into other topics. If we don't know what the component parts mean, we're going to have trouble when we get to things that are more complex. So one more set of information for you, and then I will let this be done for today. Let me grab a couple things. I need some space. All right, there's that. And I need a marker. All right. We had essentially this at some point. We had this statement right here. We were using an approximation first, but if we put that limit notation on the front, we would have an exact equal sign. So I'm just going to take that and copy it with the limit notation. A is equal to the limit as n heads off to infinity of the sum, I equals 1 to n, f of 1 plus I sets of 2 over n times 2 over n. When we did the work that way, that gave us exactly the same thing as this did. 1 to 3 f of x dx. If we took the integral, or the antiderivative of f of x with respect to x, and then evaluated with a lower limit of 1 and an upper limit of 3, we got the same answer. So I think we need to know the correspondences here about what these mean. This part here, this part on the front, where we are adding up, that summation means adding up an infinite number of little things, that is the same as this summation right here. Notice how the integral sign looks kind of like an elongated S. It's for summation. That's what's going on. This chunk right here, this f of x, is really corresponding to that chunk that has f in it also. But these are our heights. So we had individual rectangles we were considering up here, and so we took all of those heights. We had to find them and work with them. When we have the integral format of things, the height is just the function. We don't have to do any extra business with little nudges by certain amounts. This 2 over n hanging off the end of our statement, this went with width. And we wanted that to be really, really tiny. And it is. When n heads off to infinity, 2 over n heads towards 0. We get a very, very small width at any large n that we choose. So that width corresponds to this dx. Those dx's represent the width. So if you know what the parts of an integral do, then you'll be able to set them up on your own, and you'll be able to let things grow into things beyond area, like volumes when we get there. But I think it's going to be a struggle if we don't know what the parts do. So please, please, please hear me when I say, let's know about those parts. All right, for this, I am unlikely to ask you to reproduce a summation like this, like, start to finish all on your own. But I am likely to ask you things like, okay, we got here to the end. How can we work our way through something like this? Or even better, if I give you the area limit all set up, can you tell me what the component parts are? What do they do? You might have noticed that one thing that we don't see a whole lot in here, like this has the 1 to 3 on here. That gap of 2 on the number line, 2 units between our start and our end, that's hiding up here in the 2 over n. But the specifics of 1 to 3 are not as noticeable down here. Anyway, I will stop now. Please know corresponding parts for this. If you know that, that will help you grow and develop other things. I'll talk to you soon.